We're going to be looking at polynomial functions today. Vocabulary for Math 3, things about the graphs. We'll be doing a quick review of some division of polynomials, and then also looking at factoring of polynomials. So relative extrema, so when we graph these nice polynomial functions, they are continuous, nice, smooth, curved lines. And as a result of that, we have local max or min. So that's a point on the graph where it changes from increasing to decreasing or decreasing to increasing. So on the graph here, they're labeled as turning points. We call them local max or min because they are the max or min at that particular point of the graph. It doesn't have to be the overall highest point of the graph or the function there. So whatever the degree of your polynomial is, you will have at most n minus 1 turning points. So a cubic function, we could see up to 2 local max or min. It may only have 1 depending on how much of a change there is on the graph. Sometimes it's a little bit harder to see if the graph hasn't been stretched a lot. Same thing with a quartic function. I can have a quartic function that's a really nice W-shaped graph like you see here, and we have very specific turning points, and we see 3 of those. Sometimes quartic functions can be flattened out at the bottom. There's not a definitive turning point for those, and we wouldn't be able to necessarily find local max or min on a graph like that. So roots, zeros, intercepts, those terms tend to be kind of used interchangeably when we're talking about polynomial functions. Those are the places where the function is equal to 0. So graphically, here we have a cubic function. We see that it has 3 real roots because it's crossing the axis at 3 points. It's not always true that that would happen. Sometimes we have those complex or imaginary zeros. The fundamental theorem of algebra tells us, though, that whatever the degree of a polynomial is, I'm able to find that number of roots for the polynomial function. They're going to be some combination of real or imaginary. Complex roots have to occur in pairs. So if you have a function that doesn't cross the axis the same number of times as the degree, then you have some complex roots. And again, you can't have just one. It has to be 2 of those in your polynomial function. And that'll be important when we start looking at factoring polynomials. So the remainder theorem is another theorem that tells us that just specific things about polynomial functions. In this case, if I divide a function by x minus c, that is a factor, the remainder is equal to f of c. So most often you were asked to evaluate a function at a point. This is just another way for us to find function evaluations at a point. And we can do this using polynomial division. So the most common method for this is using synthetic division. So for synthetic division, we take this term x minus c and we turn it into something that would be x equals, and in this case, x equals negative 9. So that we want to evaluate that function at negative 9. And then you put your coefficients for each term in this row here. So I have a column for every term of the polynomial. Now, if my quadratic had been missing that middle term, I would have put a 0 there. I still have to have a column as a placeholder for that term of the polynomial when we do this division. If you don't do that, if you don't put a 0 at the end, if you don't have a constant term on the polynomial, then you're going to end up with some incorrect solutions. So just be really careful with your placeholders. So we're going to bring down the number in the first column. So that's our 5. And then we take and we multiply the negative 9 and the 5 to give us negative 45. That goes underneath the 3 in the second column. And then we're combining that middle column, so that's going to give us negative 42. Again, I take and multiply the negative 9 by the negative 42. That's going to give us negative 378. And then I'll add that last column. So I'm going to get negative 385. So this, when we divide, is the remainder. And the remainder theorem tells us that this is going to be equal to f of negative 9. Again, I could have taken negative 9, plugged it in place of x, and gotten that same answer. When we have longer polynomials to higher degrees. This is just a really nice shortcut to help us evaluate functions at certain values. An extension of the remainder theorem is the factor theorem. So the factor theorem just says that if I were to divide a function and get a remainder of 0, then it also has to be a factor because, again, factors, zeros, roots, all of those things kind of are related together and are a little bit interchangeable. So it just means that the function's equal to 0 at that point. So that's our definition of a factor. So again, we're going to take and we're going to put the number in the front that we're dividing by. This is not in the x equals form, so I'm going to do that and say it's going to be x equal to 2. So that's what I'm dividing by. So that goes out in the front, and then we would have our coefficients for each term of that polynomial. Leave a little bit of room. Bring down the number in the first column, 1. Multiply the 2 and the 1 to get 2. Add negative 1 and 2 to get 1. 2 times 1 is 2. Negative 1 times 2 is 1. And then 2 times 1 is 2. So we're going to double check this again. So we bring down the 1. 2 times 1 is 2. I add negative 1 and 2 to get 1. I repeat that again. So 2 times 1 is 2. Negative 1 and 2 gives me 1. 2 times 1 is 2, which means I have a remainder of 4. So my remainder is not 0, which means that this is not a factor of this polynomial. And that would be the answer that we would give. If that had been a 0, then we would have known that this indeed was a factor of that polynomial. We also need to talk about end behavior. So end behavior is just thinking about what is the function doing as it gets really large or really small. So the far right, far left side of your graph. So there's 4 cases that we see with polynomial functions. So we can have a positive leading coefficient. So again, that's on the highest degree of the polynomial that we are working with. So positive leading coefficient with an even degree would be something like a quartic function. In this case, we know that it's going to be up on both sides. So we would say that as x approaches positive and negative infinity, the function is approaching positive infinity. So the end behavior is going to be the same on both sides of that polynomial function with an even degree. If we have an even degree with a negative leading coefficient, when we think about transformations, that means that that has been reflected across the x-axis. So it flips that over. So now rather than the function going to positive infinity, now it's going to go to negative infinity on both sides. So again, thinking about what you know about, and you can even go back and think about quadratic functions because that has an even degree. But the end behavior should be the same, and then thinking about whether it's up or down on both sides. For an odd degree, the most commonly referred to polynomial function would be a cubic. And so when we have one that has an odd degree, the end behavior is going to be different on both sides of that polynomial. So that's the biggest thing that we need to remember. So because it is different, we actually have to write this as 2 different polynomial statements. So as x approaches positive infinity, the function is approaching positive infinity. As it is approaching negative infinity, the function is approaching negative infinity. If I take and reflect that function, so we're going in that direction, then the end behavior changes. So from negative infinity, the function is going up to positive infinity, and if it's going to positive infinity, the function is going down to negative infinity. So that's a lot of positive and negative infinities. If you're going to use limit notation, it looks very similar to what we have here. We just change in that we write LIM to represent limit. We would say that x is approaching either positive or negative infinity or both. and then that the function is approaching some type of either positive and negative infinity on either side of the graph. So the concept is the same. Again, it's just slightly different notation. And again, that is what we refer to as limit notation. So the last thing that we need to be able to do is factor polynomials. There are lots of strategies that you've learned for factoring polynomials. So you can graph and find intercepts. We can factor by grouping. You can factor a trinomial, quadratic trinomial using the X puzzle and the box method. Again, we can't possibly give you every single possibility. In some example problems, we're just going to look at some of the main ones that we've looked at before in Math 3. So we have a quadratic function. So what I know about polynomials is this should have two roots. So if I graph it first, I can see that I do indeed have two real roots. Now they're not nice even numbers. So in that case, I might try going back to this idea of the X puzzle. So remember the X puzzle, we said that we were going to take and multiply your A value by your C value, and that goes up here in the top of that puzzle. So I want two factors that multiply together to give me 24, that when I add them I get 11. In this case it's going to be 8 and 3. And then if you like to use the box method, your first term is going to go up here in the upper left corner, the 4 is going to go in the bottom right corner, and then we use these two numbers, we break them apart. If you were going to use factoring by grouping, it would be splitting the middle term into 3x and 8x. And then you need to find your GCF for every column and every row of your box. So 6x squared and 3x have a GCF of 3x, 8x and 4 have a GCF of 4. You just need to check at the end to make sure that these two values, so 3x and 2x, should multiply together to give me 6x squared. You just have to be careful with the signs and make sure you have negatives where appropriate. And then the last thing that you do is you take these values here. So these are your factors of that polynomial. So this one would become 3x plus 4, and this one would be 2x plus 1. And we factored that quadratic polynomial. So it's not always true, though, that we have nice ones that graph for us and give us some intercepts. So x squared plus 4 would be one where graphically I don't have intercepts, which means we're going to deal with our complex roots. So in this case, we could treat it like we are trying to find or solve this equation. I set it equal to 0, subtracted 4 from both sides. Taking the square root of negative 4 would give me positive and negative 2i. And then I write that as two separate factors there, x plus 2i, x minus 2i. So the next one, x to the third minus 5x squared plus 2x minus 10. When we graph this one, you can see that we do have a real root at 5. So you could use some synthetic division, divide by the 5, and keep working through that way. One method to remember that can be helpful, though, is factoring by grouping. So if I look at this one, I can see that the GCF of those first two terms is x squared, so I factor that out of both terms, leaving me with x plus 5. The same thing for 2x minus 10. If I factor out the GCF of 2, I now have that common factor of x minus 5. So then we factor that out because that's the GCF for those two terms. So that's where the x minus 5 comes in the third row. And then the x squared plus 2 is what's left, and so that becomes another factor. You can do that just like we did the one before. Set x squared plus 2 equal to 0, solve for x. We do end up with plus or minus I radical 2. And so we have two factors that are complex roots, one that is real. And again, we know that that's correct because we have a third degree polynomial. So I have to have three roots. I can see on the graph that one of those was a positive 5. So again, factoring by grouping doesn't always work nice and easy. So as we go to a quartic polynomial, if I were to graph this quartic polynomial, I can see that it has two real roots at -2 and 4, which means that my other two have to be complex numbers. I have 5 terms, so grouping is not going to be the easiest way for me to do this. So I like to use synthetic division. So when I synthetically divide by these real roots, this is the next degree down. So if I started with x to the 4th and I divide it by x to the 1st, I'm going to have x to the 3rd. So this would be x to the 3rd minus 4x squared plus 3x minus 12. I can divide that again by the second real root that I can see in that graph. And then when I do that, I'm left with x squared plus 3. And then I can take that, I can use that same method of setting the equal to 0. Now, again, for quadratics, you have all of those different things. Don't forget about quadratic formula as another method to help you solve quadratic equations. This one, because it only has 2 terms, is really nice and easy to solve algebraically. So I have 2 complex roots, one that is a positive and negative I radical 3, and then the other 2 real roots that I found from the graph, x plus 2, x minus 4. So again, there are lots of ways to factor. This is one of those skills that you're just going to have to practice a few different times until you kind of get into a nice rhythm, and you'll figure out kind of your preferences on that. But always going back to those key features, things that we know about polynomials, to make sure that we are finding and getting correct roots and solutions for polynomial functions.